Filtration. Filtration is a process used to remove impurities from water. It involves passing water through beds of fine granular materials like sand to remove suspended solids, organic matter and bacteria. There are two main types of filters: slow sand filters and rapid sand filters. Slow sand filters can remove a higher percentage of impurities and bacteria, but have a lower filtration rate and are more expensive. Rapid sand filters, on the other hand, are faster and more commonly used in modern treatment plants. Before filtration, screening and sedimentation are used to remove a large portion of contaminants. Coagulants can enhance the removal of fine particles. However, even after these steps, some impurities may remain. Filtration helps to further purify the water by removing color, odor, turbidity, and some pathogenic bacteria. After filtration, disinfection techniques are applied to kill any remaining germs and remove color. Overall, filtration is an important step in water treatment, ensuring that water is safe and suitable for consumption. Filtration works by purifying water through four processes, অর্থাৎ চারটা প্রসেসে কাজ করে। 1. Mechanical straining. 2. Flocculation and sedimentation. 3. Biological metabolism. 4. Electrolytic changes. Mechanical straining. Larger particles in the water are unable to pass through the gaps in the filter's sand layers. They get trapped and removed, resulting in cleaner water. Most particles are captured in the upper layers of the filter, forming a mat that aids in straining out impurities. Flocculation and sedimentation. Even smaller particles which can pass through the filter's gaps are effectively removed. The void spaces in the filter act like small tanks where the particles become trapped and form a gelatinous mass. The mass attracts other fine particles, causing them to settle down and get removed. 3. Biological metabolism. Filters contain microorganisms and bacteria that reside within the voids. These organisms rely on organic impurities present in the water, such as algae and plankton, as their food source. As they consume these impurities, they convert them into harmless compounds through biological processes. A layer called or dirty skin forms on filter surface, assisting in absorbing and straining out impurities. Electrolytic changes. Filters can alter the water's chemical characteristics through electrolytic processes. The sand grains in the filter media and the impurities in the water can carry opposite electrical charges. When they come into contact, these charged particles neutralize each other, leading to a change in the water's composition and making it purer. Eventually, the electrical charges of sand grains becomes depleted and the filter needs cleaning to restore its effectiveness. Together, these processes contribute to purification of water in filters, ensuring the removal of impurities and providing cleaner and safer water for various purposes. Filter materials such as sand and gravel are commonly used in water filtration systems. Sand is the primary filter media and it should meet certain criteria. 1. It should be free from dirt and impurities. 2. The sand should have a uniform size and nature. 3. It should be hard and resistant. 4. After being treated with hydrochloric acid for 24 hours, it should not lose more than 5% of its weight. The size of the sand is measured by effective size, which is the size of sieve through which 10% of the sand sample will pass by mass. The correct effective size is crucial for optimal filtration. If the size is too small, the filter will clog frequently and have lower filtration rates. If the size is too large, suspended particles and bacteria may pass through without being removed. The effective size for slow sand filters typically ranges from 0.2 to 0.4 mm, while for rapid gravity filters it ranges from 0.35 to 0.55 mm. The uniformity coefficient is a measure of the size variation of particles and is expressed as the ratio of the sieve size through which 60% of the sand sample will pass the effective size. For slow sand filters, the uniformity coefficient D60 by D10 typically ranges from 1.8 to 2.5, while for rapid gravity filters it ranges from 1.3 to 1.7. Gravel is used to support the sand layer and allows water to move freely to the under drains. It should be hard, durable, free from impurities and properly rounded. Different sizes of gravel are typically placed in layers, with the coarsest size at the bottom 20 to 60 mm and the finest size at the top 3 to 6 mm. This layered arrangement helps in achieving effective filtration. Slow sand filter. Slow sand filters were created in 1829 by James Simpson and were widely used until the late 19th century. However, they are not commonly used anymore because newer filters are faster and more efficient. Slow sand filters may still be used in smaller plants in warm places, where freezing is not a problem. These filters take in water from sedimentation tanks and are used for treating better quality water. Rapid sand gravity filter. Slow sand filters have a very slow filtration rate, which means they require large areas for installation. They also need a significant amount of filtering materials, making them costly and impractical in congested cities and industrial areas. To address these challenges and improve filtration speed, researchers developed rapid sand filters, also known as mechanical sand filters. Rapid sand filters come in two types. 1. Rapid gravity filters. These filters use larger sand particles, allowing for a faster filtration rate compared to slow sand filters. They are commonly used for large municipal water supplies. 2. Pressure filters. These filters utilize pressure to increase the filtration rate. They are more compact and convenient, making them suitable for smaller installations like industrial plants and swimming pools. Pressure filter. Pressure filters are smaller to small rapid gravity filters but are housed in closed containers. Pressure filters are similar to small rapid gravity filters but housed in closed containers. Water to be treated is passed through these filters under pressure, which is higher than atmospheric pressure. To ensure effective filtration, the pressure filters must be located in airtight vessels. Raw water is pumped into the vessels using pumps, and the pressure applied typically ranges from 30 to 70 meters of water head, which is equivalent to 300 to 700 kN per meter square. Efficiency and suitability of pressure filters. Pressure filters are not as effective as rapid filters in removing bacteria and turbidity from water. The quality of the filtered water from pressure filter is lower, so they are generally not used for public water supplies. However, pressure filters are compact and easy to handle, making them suitable for treating smaller amounts of relatively clear water. As a result, they can be installed in situations such as small residential areas, individual industries, private estates, swimming pools, and railway stations. Disinfection or sterilization. Disinfection or sterilization is a crucial process to make water safe for drinking by killing harmful bacteria. It is the most important step in water purification because bacteria can spread diseases and cause public health emergencies. Even if the water is clear of turbidity, color, or minerals, the presence of a single harmful organism can be dangerous. Disinfection is not only performed at the water treatment plant but also ensures continuous killing of bacteria in the distribution system, preventing contamination during transit. The disinfectant used should be provide a residual sterilizing effect for an extended period to protect against recontamination. Chlorine is widely used as the most effective disinfectant worldwide and commonly referred to as chlorination. Other minor disinfection methods exist, which also be discussed separately. The disinfectant should be harmless, tasteless, cost-effective, and easily measurable through simple tests. Minor methods of disinfection. Minor methods of disinfection include 1. Boiling of water. Boiling water for a certain period of time kills most types of bacteria and viruses. It is a simple and effective method but may not be practical for large-scale water treatment. 2. Treatment with excess lime. Adding excess lime to water raises the pH level, which can disinfect the water by killing bacteria and other microorganisms. Lime treatment is commonly used in small-scale applications. 3. Treatment with ozone. Ozone is a powerful oxidizing agent that can kill bacteria, viruses, and other harmful organisms. It is commonly used in water treatment plants and requires specialized equipment for its generation and application. Treatment with iodine and bromine. Iodine and bromine are chemical disinfectants that can be used to treat water. They are effective against a wide range of microorganisms but may leave a residual taste and odor in the water. Treatment with ultraviolet rays. UV radiation is used to disinfect water by damaging the DNA of microorganisms, rendering them unable to reproduce. UV disinfection systems are commonly used in homes, hospitals, and small-scale water treatment facilities. Treatment with potassium permanganate. Potassium permanganate is a chemical disinfectant that can oxidize and kill bacteria and viruses. It is commonly used for emergency water disinfection. Treatment with silver. Electrocatadine process. The electrocatadine process involves using silver ions to disinfect water. Silver has antimicrobial properties and can effectively kill bacteria and other microorganisms. These minor disinfection methods are often used in specific situations where other disinfection methods may not be readily available or practical. The choice of method depends on factors such as the scale of treatment, water quality, and specific requirements of the application. Types of chlorination and certain important definitions. Types of chlorination and certain important definitions. 1. Plain chlorination. Plain chlorination refers to the process of adding a specific amount of chlorine to water for disinfection purposes. It is the basic form of chlorination without any specific consideration regarding timing or additional treatments. Pre-chlorination. Pre-chlorination involves adding chlorine to water before any treatment processes such as sedimentation or filtration. It is done to control algae growth, reduce odor, and remove some organic impurities present in the raw water. Post-chlorination. Post-chlorination is the process of adding chlorine to water after the primary treatment processes like sedimentation and filtration. Its purpose is to ensure disinfection and maintain a residual level of chlorine throughout the distribution system to prevent the growth of microorganisms. Double chlorination. Double chlorination refers to the practice of adding chlorine twice during the treatment process. It can involve both pre-chlorination and post-chlorination or two separate doses of chlorine during the treatment stages. This is done to achieve higher levels of disinfection and ensure the safety of the water supply. 5. Breakout point chlorination. Breakout point chlorination is the process of adding chlorine to water until it reaches a point where it reaches all the organic and inorganic substances present, thereby eliminating any excess chlorine demand. This process helps in achieving effective disinfection and removing unwanted contaminants. Superchlorination. Superchlorination, also known as shock chlorination, involves adding a significantly higher dose of chlorine to water than the usual disinfection dose. It is typically done as one-time treatment to eliminate persistent microbial contamination, disinfect the distribution system, or control biofilm formation. Dechlorination. Dechlorination is the process of removing or neutralizing chlorine from water. It is often performed after disinfection to make the water safe for various purposes, such as releasing it into the environment or using it in industrial purposes where chlorine could be harmful. This different type of chlorination and release definition helps water treatment professionals effectively manage the disinfection process and ensure the safety and quality of treated water. The specific type of chlorination chosen depends on factors such as water quality, treatment objectives, and regulatory requirements. The advantages and disadvantages of using ozone as disinfection are discussed below. Advantages of ozone as disinfectant. 1. Ozone rapidly decomposes and leaves no residue in water by the time it reaches the distribution system. 2. Ozone effectively removes color, taste, and odor from water in addition to eliminating bacteria. 3. Water treated with ozone becomes pleasant tasting, unlike chlorinated water, which can have a bitter taste. Disadvantages of or limitations of ozone. Ozone treatment is expensive, often more costly than chlorination. Ozone production requires electricity, limiting its use to areas with readily available and affordable power supply. 3. Ozone is highly unstable and it does not have residual disinfection in the water. This means there is no long-lasting protection against potential future contaminations. While ozone offers benefits in terms of effective disinfection and taste improvement, its high cost, reliance on electricity, and lack of residual protection are important considerations in declining its suitability for water treatment applications.